Kia ora Year 13. I'm going to start working through last year's probability distributions paper, and I've already done 1A. So this is the second part of the question, which is all about cars and their GPS systems, which was, I thought, quite a nice context. So we're told that car drivers have got different mobile phone navigation apps. I'm going to show you how I'd highlight as I were going through. And they're used to get an estimate of the time it will take to travel to a destination. Study was carried out to investigate how accurate the time travel estimates were from one particular GPS app. For each trip in the study, the estimated travel time was compared to the actual travel time. And the absolute difference, that gets 2 underlines, was calculated. And we're given some of that information in the table below. So this is just to give you a wee bit of context about what it means by the absolute difference. For example, if we had a trip where the GPS thought it was 10.4 minutes, but it turned out to be 11.3 minutes, the absolute difference is 0.9 minutes. Okay, so that's one where the estimated time is less than the actual time. The number we get is 0.9. This one here, the next one down, the estimated was 6.5, but the actual was 5.2, so the estimate was too high. The absolute difference means that all we care about is the gap between the two numbers, not whether there's a positive or a negative. So that one's 1.3. Now that doesn't matter too much for the easy part of the question, but you've got to understand that to get much further. So the first question is this. Suppose that 15% of trips made during the study were classified as not accurate, using the absolute difference. If 10 trips were chosen at random, using an appropriate model, which means choose a distribution, calculate the probability that at most 4 of the trips were classified as not accurate. So let's think about which one it's going to be. We've got 5 to choose from: binomial, uniform, rectangular, Poisson, and normal, right? Burp in case you're having trouble remembering, which at this point in the year you really shouldn't be. Here, it fits a binomial. And you're going to be asked why later in the question. It fits a binomial because we've got 2 things that could happen, either not accurate or accurate, and we're given a probability of whether it's not accurate as 15%, right? So that's the basic reasoning behind why it's binomial. So let's figure out what they're trying to get us to work out. What's the chances that at most 4 of the trips were classified as not accurate? So we've got a binomial situation. A random variable x is distributed binomially with n of 10 and p of 0.15. So just check that we're looking for at most 4 not accurate, and not accurate matches up to this probability here. So what we've got to work out is the probability that x is less than or equal to 4. Right? At most 4 means we can include 4. Now I haven't got a graphics calculator emulator on my home computer, so I'm just going to quickly scribble down the buttons that you push on your blue calculator. So you're going to go menu, stat, dist, then you choose binmer. Remember we're looking for a cumulative probability, so it's going to be BCD. Make sure your calculator's in variables, not list. And then you're going to choose n equals 4, or no, I think it's num trial equals 4. Whoops, no, sorry, x is equal to 4. Num trial is our n, so that's 10, and then p is 0.15, and then hit go. So the probability that x is less than or equal to 4 is equal to 0.9901, and that's to 4dp. Okay, so that's the achieved part of the question. The next part of the question asks us to talk about our choice of distribution. Okay, so justify the use of the probability distribution for your answer in part 1. All right, so to speed this up a little bit, what I've decided to do is to type up what I would write in the exam and then to talk about it, okay, instead of writing it out really messily. But you need to make sure that everything you're doing for this part of the question is in context. So the first 2 things that are the easiest to talk about with the binomial are that we've got a fixed number of trials. And the second thing is that there are 2 outcomes. It's not enough just to say, oh, we've got 2 outcomes. You need to put it into context. So what I've done here is that I've said we're looking at 10 trips. You must link it to the context. Have I said that enough times? Maybe not. Right. And then the second thing, the two outcomes are accurate or not accurate. Now, if you gave those two and you wrote them in context, you're going to get merit. But I would keep on going because we've got 4 conditions for a binomial and they're super easy to write up here. So the probability of a trip not being accurate is given to us as 15%. So the probability of success is constant, right? Again, you've got to link it in to the fact that we're looking at GPSs and car trips. And then the other useful thing that you might not have picked up in the question wording is that up here, it said that 10 trips were chosen from the study at random. So that at random is really important because it means that because the trips have been chosen randomly, we're more likely to have our condition that the outcomes of the 10 trials are independent, right? You might expect that if it had been 10 trips chosen in a row, that independence wasn't satisfied as well. Okay, so that's all of the merit part. Now, the next part of the question is the harder part. So here it comes. Right, the mean absolute difference between the estimated travel time and the actual travel time was 3.5 minutes with a standard deviation of 2.8 minutes. And the study also found that 87% of trips had absolute differences of less than 5 minutes. And you need to talk about 2 reasons why it would be stupid or inappropriate to use a normal distribution to model the absolute differences between the estimated and the actual travel time for trips. So let's go right back to the start of the question and look at this table and think about what those absolute difference numbers are going to look like. Because all we care about is the gap between the 2 things, they've given us one where the actual and the estimated are the same. And so the difference there is 0. The key to doing well in this question is getting that we can never have a negative number. So you've got to give 2 reasons why the normal distribution wouldn't work. And they're not all to do with the fact that you can't have negative numbers, but that's going to help you a lot. So the first reason here is that we have a normal distribution is symmetric. So I'm going to give you some headings to help you think about questions like this. And the first heading is symmetry. So normal distribution is symmetric. So the normal distribution is symmetric, but this distribution shouldn't be symmetric because the minimum is 0, and you might expect it to look like this. You'd think that most of the times would be pretty close, but some will be way off. So I would expect that a distribution for this in real life would look much more like that. So that's the first thing. Okay, so it's in context. The minimum 0, most trips pretty accurate. So symmetry is always a good thing to talk about if you're asked to comment on a normal distribution. So the next thing to look at in this question is to tackle the thing about 0. Now they've actually split it up into 2 marks in the schedule, but they're kind of the same thing. The idea here is that a normal distribution is going to give us some proportion that's negative times. Okay, so this is what I think of as 0.2, but they've split it up into 2 and 3. So if we've got a normal with mean of 3.5 and a sigma of 2.8, this will predict some negative times. So some negative mean absolute deviations, or mean absolute differences, I think they're called. But this is impossible in real life. Now, we can work out with the model what's the probability that x is less than or equal to 0. And if you chuck that into your calculator, you get 0.1056. So 11% of the time, this model generates forecasts of negative mean absolute deviations. So that's not very good. Now, the next thing you can do is you can compare. So you can think of this as, you can call it unboundedness or the zero factor. Right? The normal distribution is not bounded at either end, but in reality, it is here. It should be bounded at 0 at the lower end. The last thing, and actually the easiest thing to do here, is to compare the model with what actually happened in real life. So the study found that 87% of trips had absolute differences of less than 5 minutes. It's always a good thing to do to compare that actual thing, the experimental number, with the theoretical or model number. Okay, so here we've got the probability that x is less than 5 is equal to 0.704 using the model. Okay, so using the normal model. But in the study, the number was 87% were within 5 minutes. And that's a significant gap. Okay, so let's try and sum that up for what you can generalize to another question if you're looking at the normal distribution. Well, the first thing to think about is symmetry. The second thing to think about is unbounded. But don't get into stupid things here, right? There's no point saying that, you know, in theory we could have infinitely high with the normal, because the probability of that happening is going to be really small. But here we had a significant chunk, or about 11%, that were going to be negative. That makes no sense. The third thing is to compare the model versus the actual. And that's a really good thing to do in real life as well as in stats exams. Now, I know this has been quite long, but I'm hoping that I'm helping with some of these questions that you guys think of as quite waffly and quite hard. I'll do the rest of the probability distributions paper later on tonight. Please let me know if there's any other specific question you want done over the next couple of days.